So in this part, we're going to talk a little bit about the remaining parts of designing a good experiment, what it means to have a placebo effect, and why we blind in an experiment if we can. We're going to talk about statistically significant and also look at blocking and matched pair design. Just a reminder about the principles of experimental design, that there has to be a comparison. It can't just be one group of people being checked pre-test or post-test. You have to have a baseline, and that's normally called the control. And sometimes the control gets no treatment, and sometimes it gets the most common thing. So we can check to see if the most common thing is different from the new thing we're checking out. Random assignment. We randomly assign so we can make sure we offset any of the other variables that might affect our ability to infer causality. And then we control the rest of them. So we've talked about little different things in that. And then replication, there has to be enough experimental units for us to be able to mitigate the effects of chance, or we can do the whole experiment a second time or a third time. We randomize, and we treat the subjects the same in every way except for the one thing we're testing, which is our treatment. There has been very clear evidence of something called the placebo effect, so the placebo effect is very much that the human mind, if you believe that something is going to affect you, it will, and if you believe something will not affect you, it won't. Not that you have that complete power over it, but there is definitely research that shows that the placebo effect exists. So researchers need to, if possible, make the subject design or the experimental design to have the ability to blind. And that means that in a blind experiment, the subjects don't know what treatment they're getting. In a double-blind experiment, neither the subject nor the researchers know. So let's say we were doing something related to coffee here. The barista could be over here in the corner, and they would know what was going on. They would know, for example, that the one with the extra picture was caffeinated, and the one without the extra picture was not caffeinated. And this subject would be randomly put into this group, and this other subject be randomly put into this group. And the subjects would know which one they were getting. The person doing the face-to-face research wouldn't know which one they're getting, but this person knows. And that double blind allows the placebo effect from thinking that something's going to happen to you in the subject's case, or the researcher treating someone as if they think something's going to happen to them. And that way it's as neutral as possible. So when we are done with our experiment, we've collected our data, we need to decide after we've done some analysis whether the results are large enough to be considered statistically significant. And that just means that whatever happened would be unlikely to happen just because of chance. So when we are looking at the results, we will do some simulations to decide if what happened happens frequently by chance or rarely by chance. And if it happens rarely by chance, then we consider it statistically significant. And I'll give you an example. There's an example on page 249 to 251, so if you'd rather read it instead of listening to me blather, you're more than welcome to. They were trying to decide, their question was, does distraction affect your driving? Specifically, does distraction affect your driving where the treatment was considered cell phone use while you were driving, and the control was considered just having someone in the car to talk to? So the explanatory variable in this case was distraction. The response variable was an interesting one. It was a categorical variable. Did they stop at this rest stop that they were supposed to stop at? Now this was a simulated, you're driving in a simulator, but still that probably makes it a little safer, a little more ethical than having people randomly driving out on the road. And people were randomly assigned to groups, and in this case there's just no way for the designed to include blind. You either know that you have a cell phone that you're talking on, or you have a passenger with you. So there's no way for there to be blinding in this case. So this is what happened. To decide if it's statistically significant, we're basically asking the question, is it so weird that it can't be explained away by chance? And so when we're doing This is called a hypothesis test, and we'll do a lot more of those later. But basically, always our hypotheses start with a null hypothesis, which means the types of the distraction will have the same effect on the rate, in this case, where they remember to go to the rest stop. And the alternative hypothesis is what we think is going to happen. In this case, that the types of distraction will have a different effect on the rate, and we expect that the cell phone will have a lower rate of remembering. And sure enough, when they collected the data, half of the people that were talking on the cell phone forgot to go to the rest stop, whereas only 3 out of the 24, or 1/8 of the people, didn't stop at the rest stop if they were chatting with the passenger. So this is the result. Now the question is this result so large that it wouldn't happen very often by chance? So we are going to check to see if the results are statistically significant. We can run a simulation. And since in this particular experiment there were a total of 48 people and 30 people remembered to go to that rest stop, remember that's a response variable, and 15 did not. And so we're going to create cards based on those 48 people, 33 yes cards and 15 no cards. And since we are simulating the assumption, the null hypothesis assumption that the treatments do not affect the remembering, we're going to go ahead and put all of the results into one pile, shuffle them up, and then randomly put them into 2 piles, the cell phone distraction pile and the passenger distraction pile. Then we're going to count what happens in the cell phone pile and look to see how many yeses there are and how many no's. So let's say in the first time we've done this, oh man. So phone ring telling us to vote for a certain mayor. Anywho, let's say that the first time we simulated this, we in the cell phone pile there were 6 people that forgot. So we would go ahead and put a dot on 6, and then we would run that simulation again. And we want to run simulations at least 40 times, ideally 100 times, ideally more than that. And of course there's apps for this, but we're going to run them by hand. I'm going to give you the results of 100. So the simulation was run 100 times. The 33 yeses and the 15 nos were put in a pile, shuffled together, and put in cell phone or passenger, and only once, 1 out of 100 times, did a 12 happen just randomly by random chance. So that is this result of 12 out of 24 forgetting the rest stop would be considered statistically significant because it only happened 1 out of 100 times when it was done by random chance. And in general, 5%, anything below 5% is considered statistically significant. But there are other levels that we hold it to depending on the situation. But at 1% definitely is considered statistically significant. So when we think that there are groups of individuals within our sample or within our population that we want to mitigate for the effects that their certain qualities have on the experiment, then we put them in stratified groups that are called blocks when we do it in experiments. And those blocks are not random. They are not random. They are placed in those blocks based on their needs. So for example, if we're doing an experiment about typing speed and we think a certain keyboard might be better than another keyboard, but we think it would make a difference if they already were users of a smartphone as opposed to non-smartphone users, then we're going to go ahead and place them in blocks based on that. And then here's where the random assignment comes in. If there's any other mitigating factors that might be part of those groups, and then we're going to randomly assign them to the treatments of keyboard A and keyboard B. And then after that, what we're looking for is the response variable of comparing typing speed. Then you're going to go ahead and combine those results. And sometimes we combine those results by looking at means and the difference of the means. We might look at the difference of the medians. There's a bunch of different ways that we can look at that, but we combine the results to see if there was a difference between keyboard A and keyboard B, for example. So that's blocking. And it says matched pairs design, which the idea is to create blocks by matching pairs of similar experimental units. So if we were looking at someone who is 5'5" and 150 pounds and a female, we might try and find another 5'5", 150-pound female, and one would get the treatment and one would not get the treatment, or one would get the control and one would get the treatment. The other option for a matched pair is to have the same person do both of the treatments at different times, and the randomization would happen with who got what treatment first. So you wouldn't know ahead of time if you were going to get treatment A or treatment B. You'd flip a coin or something, and then you would know which it is. We're going to do an example of that as well. So there's all of our experimental stuff. Go ahead and read the end of that chapter summary as well, 4.2, and we'll talk a little bit about 4.3 later. Bye.